Okay, so Unit 10, Worksheet 3, Coulomb's Law, problem number 11. Three charges are placed as shown below. Determine the magnitude and direction of the net electrostatic force on charge Q1. As part of the solution, include a force diagram. So what we have here is we have charge Q1 on the bottom right. Immediately left of it is charge Q2, and to the left and above it is charge Q3. First thing that I can see is it looks like it's equidistant between charges Q1 and Q2, and between charges Q2 and Q3. So if we were to make a triangle out of that, this would be a right angle here, and these two sides are the same magnitude. Now, the fact that these two have the same magnitude or the same length means that these two angles here should also be equivalent. So that means that this is going to be a 45, 45, 90 triangle. We can use that to determine the length between charge 1 and charge 3, or we can just use Pythagorean theorem. But what that would end up meaning is that square root of 18 meters is the length between charge 1 and charge 3. The reason why that's going to be important is if we're trying to determine the net electrostatic force on charge Q1, we'll need to determine, well, the electrostatic charges between Q1 and Q3 and between Q1 and Q2, and then combine them using a force diagram. So we would need to know the distance between them. The first force that I'm going to have is our electric force between charge Q1 and Q2. So charge Q1 has a charge of positive 4.5 times 10 to the negative fifth coulombs. Charge 2, negative 1.2 times 10 to the negative fifth coulombs. And then we have Coulomb's constant of 9.0 times 10 to the positive ninth. Newtons meter squared over Coulomb squared. All of that divided by the distance between them squared. The distance between 1 and 2 is 3 meters squared. When we do the same thing for between 1 and 3, charge 1 still has that same charge of positive 4.5. Let me actually do a better 5 than that. Times 10 to the negative fifth coulombs. Charge 3 has a positive 1.8 times 10 to the negative fifth power coulombs for its charge, but Coulomb's constant stays the same. And then the distance between those two is the square root of 18 meters, and that whole value gets squared. When we plug these numbers into a calculator, the value that we get between charge 1 and charge 2 is negative 0.54 newtons. Between charge 1 and charge 3, positive 0.405 newtons. Now, that does not tell us the direction. What that is telling us is that between charge 1 and charge 2, it is an attraction. Between charge 1 and charge 3, it is a repulsion. So I'm going to put the force diagram up on the top of the screen just to try and make it a little bit easier to see. So this dot right here is going to represent charge Q1. Charge Q1 is attracted to charge Q2. So we would have that electric force on charge 1 by charge 2 pointing to the left. Now, charge 1 and charge 3 are repulsed by each other. So charge 1 would have a force that is being applied in the opposite direction between those two. That would be our electric force on 1 by 3. We have the quantities for both of these values. We know how long those force vectors are. However, we cannot ultimately decide on, well, what the combined force is going to be until we break these up into their horizontal and vertical components, combine them, and then ultimately determine where they're going to go. Fortunately, it looks like force electric on 1 on 2 is going to be already on our x-axis, so we don't need to do anything to that. We just need to break up force electric on 1 by 3 to its horizontal component and its vertical component. Now, we know that because charge 1 and charge 3 are connected on this line that's at a 45-degree angle. That means that this angle right here between our vertical and the force vector on 1 on 3 is also 45. So we can make the assumption that 45 and 45 means that both our horizontal and vertical components are going to be the same magnitude. So that would be another 45, 45, 90 triangle. What I mean by that is I'll draw what it looks like right here. But if this right here is going to be our electric force, which we're saying has a magnitude of 0.405 newtons. This is its vertical. This is its horizontal. We know that where the horizontal and vertical meet is a 90 degree, but we can also say that these two things should be equal because this and this should both be 45 degrees. So we have the length of the hypotenuse, and we have the angle. All we need to do is to determine the length of one of the sides, and then that can be the same as the length of the other side. So let's just go for the vertical component of our electric force here. So that is going to be a side that, let's say, let's go with this one. It will be our adjacent. So we have our adjacent, we have our hypotenuse, and we have our angle. In order to solve for the adjacent, we can use our cosine. So cosine of our angle is equal to our adjacent over our hypotenuse. In order to solve for the adjacent, we multiply both sides by the hypotenuse. So our electric force in the y direction is equal to our adjacent, which is equal to our hypotenuse of 0.405 newtons times cosine of that angle 45 degrees. So our electric force in the y direction resulting from charge 3 is going to have a magnitude of 0.286 newtons. So that right there is going to be our vertical and horizontal components. So when we end up combining our horizontal components, where one is going to have 0.286 newtons here, to the right, 0.54 to the left, and then 0.286 down. Overall, we're going to have a downward force still of that 0.286 newtons. When we combine the left and rightward forces, we end up with a magnitude to the left of 0.25. So for our forces here, we have a leftward force and a downward force. In order to combine them, like our vectors, what we are going to be doing is we are going to be showing that we have that downward force as one side of a triangle, 0.286 newtons. And then we would have our leftward force, 0.25 newtons. And then the combined effect of those is just a, well, tail to head force diagram that we have here, and that is going to be our net electrostatic force. Once again, this is just going to be a triangle. We can use Pythagorean theorem to determine what our net force is going to be. Our net force, well, for Pythagorean theorem, it's the hypotenuse squared is equal to a squared plus b squared. So square of one side plus the square of the other side is equal to square of the hypotenuse. So our net force is equal to that 0.25 newtons squared plus 0.286 newtons squared, and it is the square root of all of that. So the magnitude of our net force is going to be 0.38 newtons. That's the magnitude. We know overall it's going to be bottom left, but what we can actually do is we can end up determining this angle that the force is going to be applied against by using, once again, another trigonometric relationship. At this point, we have all three sides of a triangle, so it just boils down to choosing two of the sides and choosing one of our trigonometric relationships. We've been using tangents a lot with this problem, so I'll just continue with our tangent. tangent of an angle is equal to our opposite over our adjacent. So if we want to determine the angle, it's going to be the inverse tangent of the opposite over the adjacent. Our opposite side is the 0.25 newtons, and our adjacent is 0.286 newtons. When I grab a calculator, 0.25 divided by 0.286 is 0.874. And then the inverse tangent of that would give me 41.2 degrees. Well, that's 41.2 degrees for this angle right here. But that is going to be some angle beneath that. So I can do 90 minus that 41.2. And I'm going to have for my angle 48.8 degrees, and I'm just going to say southwest. Or we can say that's in quadrant 3. But when we're talking about our magnitude and direction, the magnitude is 0.38 newtons, and the direction is 48.8 degrees southwest, or in quadrant 3.